All right, excellent. So good, well, morning, afternoon, or wherever you are in the world. It's morning here in Kansas, but not unduly so. It's 9:30 here. And we're going to tell you about some work we have done in different constellations and with some other editors as well on deep deductive reasoning over semantic web logics. So this will be a kind of overview-ish tutorial, and we'll take turns presenting. I'll go first, and I'll tell you about the sequence towards the end. So I'm going to give you a general motivation, kind of why are we doing what we were doing, and then the others will dig into the technical details. My name is Pascal Hitzler. I'm at Kansas State University, and the other presenters are Eberhart, who is at my lab, Monireh Ebrahimi from IBM, and Federico Bianchi from Bocconi University in Italy. So, well, this is the neurosymbolic learning and reasoning workshop. I probably don't have to talk too much about motivating neurosymbolic AI, but I just want to give you a little kind of piece of information which we collected and put out in an overview article in AI Communications this year. We went through the key AI conferences, or some of them, ICML, AAAI, IJCLR, NeurIPS, and also IJCLR, and essentially looked at what did we find in papers which clearly do neurosymbolic topics. I'm very sure we missed some. Because you know it's a ton of volume, but we did the count over the last 10 years, and this is what we found. And you see that there is a very significant rise recently in number of papers on this general topic, which just underlines, you know, with data what we already feel, namely that there is something coming and something developing. Of course, this is only the tip of the iceberg. These conferences have very low acceptance rates. There's a ton of events also around it, which are just starting now, different workshops, for example, other conferences having more on the topic, and so on. So this is nice, because I think the topic is very exciting, and also I've been there for quite a while, so as I'll tell you in a bit. So what is neurosymbolic about? It's about combining the artificial neural network side of artificial intelligence and the symbolic logic side of artificial intelligence. Or if you want to put it in a little bit of wider perspective, not only the symbolic logic, but whatever, symbolic computation, term manipulation, term rewriting, all these kind of things, which can actually, if you want, often be captured in logical terms, even though they're sometimes not. But I think the core has really to do with knowledge representation in the form of formal logics. And why would you want to do this? You want to do this, well, there may be different reasons, but let me give you some. And one of them may be that you want to get the best of both worlds. So something like combining a very powerful machine learning paradigm that is robust to data noise, which are, of course, advantages of artificial network systems, particularly deep learning these days, but which are, well, not so well done, or rather poorly done in many cases, by symbolic systems, by knowledge representation systems. On the other hand, you would like to have things like easy understandability and assessment, explainability by humans. You want to actually sometimes really manipulate symbols for your problem solving. And you may want to be able to really seamlessly get background knowledge, expert knowledge, which you have already captured into the picture. These are all things where knowledge representation systems excel. They're really good at that. But we all know that deep learning systems and related systems are really poor at those. So one of the general motivations is combining the best of both worlds, essentially. And one of the questions you can now ask is, how do you do that best? And perhaps that's the big quest, right, we're right now in. And if you look out, also the article I just mentioned, there's a ton of approaches for doing that, combining them, endowing one system with the capabilities of the others, or having them kind of reason back and forth, etc., or adding connectionist learning to symbolic reasoners. And I think right now we're only starting to understand what can be used for what purpose. Little bit of history. You know that Arthur is one of the drivers of the event we're currently at. And And in fact, the two of us started the workshop series, the NeSy series, 17 years ago or 18 or something like that. I contacted Arthur back then and said, let's do that, because I knew he's interested in that. And I was interested in that topic, although at that time it was a very, very niche topic, and now it's bubbling up into the mainstream. And here's a couple of pointers, the first two in particular, which give more of a historic perspective. As you've seen from the first slide with the table and the paper numbers, the topic is really picking up speed since 2017. So keep that in mind when you look at the old stuff and also the new stuff. I also think that some things have changed in terms of what it's doing, not only the emphasis on deep learning, but there's consequences from that as well. Simply because you can now do more things with artificial neural networks than you were able to do 15 years ago. This is a little bit of a pre-announcement. We, in that case, Kameruzum and Sharker, who's now at University of Hartford, and myself, we're editing a book on neurosymbolic artificial intelligence, the state of the art. It's invited chapters by people who have contributed. And this is just a teaser. This should come out early next year. So we're in the final stages of producing this, and should give a nice overview by the contributors who are essentially surveying their own piece here. And since we have prominent people doing this, this gives a nice overview, kind of keeping all together. All right, so deep deductive reasoners. This is now, it's a part of the neurosymbolic AI landscape. And well, it's one which is particularly dear to me. And you can, of course, ask what are you doing there, and why are you doing it? So the key thing here is that we're training deep learning systems to do deductive reasoning in the sense of formological deductive reasoning. And of course, you can ask, why is this interesting? Why would you do that? Well, I think there's a fundamental answer to that before I come to the technical ones. And the fundamental answer is that if you want to combine those two approaches, the symbolic and the neural, and we've had motivations for that earlier, then in fact, deductive reasoning is at the heart of logic-based knowledge representation. So it's the key task you do algorithmically there. So from that perspective alone, it's interesting to see, can we do that by learning it? You can also look at it from a cognitive science perspective. You can say, well, our neural brains can learn to do highly symbolic tasks like formal logic and reasoning, or in more general in mathematics. So how can we have artificial neural networks which can do that? So that would be from the perspective of understanding human cognition. But there are also technical motivations which come more kind of out of the computer science perspective. And those would be that you may want to be able to deal with data that contains noise. So errors, these kind of things, whatever real data has. Symbolic reasoners usually do very poorly with those. You may want to do it with speed, because these symbolic reasoning algorithms are very high complexity. Kind of people who are not so familiar with this usually think, well, NP is bad. Well, for us, NP is kind of only moderately bad because we have non-deterministic exponential time, and even worse for these algorithms sometimes. So in the worst case, there's a speed problem. And then, yeah, okay, I mentioned that already. Out of principle, right? We may want to learn about capabilities of deep learning for complicated cognitive tasks. You may also want to do it for easier combination of deductive reasoning with more traditional learning tasks, which you do in deep learning, because then you have both in neural networks, and you could start combining them in various ways. So there's more than those, but I think these are some of the key ones. Now, how can you get at the reasoning problem through deep learning? And I think there's two generally different setups. And one is that you think of reasoning as a classification problem. So reasoning means you're given a set of logical formulas, a theory, and well, once you have that, then any formula expressible over the same language is either a logical consequence or not a logical consequence of this theory. And here you have your classification problem. And now, since we have symbolic reasoners which can do that, right, it's as easy as just, well, producing a ton of training data, which you can do algorithmically, set up your pet deep learning system and just train it, right? Well, no, because it turns out to be a really hard machine learning problem. And this will be probably one of the takeaways from what we're showing you today, because it will be a mix of well, good, really, really strong systems doing that, and a mix of, well, things that are not so good, simply because it's a hard problem. Here's another perspective, and that's probably a more interesting one. From the logical perspective, you would call this something like knowledge materialization. The idea here is that, again, given a set of logical formulas, you want to produce all logical consequences, well, under certain constraints. You need to have these constraints because the set of all logical consequences is generally infinite, but you can put some reasonable constraints like length and stuff like that. Well, so you want a neural network that learns to produce them all such that you don't have to query, because generally you're interested in what are the logical consequences. And if you have only a classification system, that means you have, for all candidate consequences, you have to query the system. That doesn't sound very speedy, and usually isn't. So you would like to have a system that produces all of them. And this is, of course, the one which is much more interesting for potential applications of this approach. All right, almost at the end here. This is an overview over published deep deductive reasoning work we know about. I just want to tell you about the columns here because they're interesting, they're important for the discussion. By the way, I'll post a link to these slides and also to the other slides after my part in the chat, so that you can also have the things offline, because there's also references. As you can see here, they're at the end of these slides. So logic refers to kind of which logic are you looking at? And there's a ton of different logics. One important aspect here is to understand that these logics are of different level of difficulty for automated reasoning. And the most straightforward way to assess that would be to look at computational complexity. But there is also another, not a strict measure, which is sometimes called expressivity. It's kind of how expressive does the logic feel? How easy is it to put your problems into this language? And it is completely possible that two logic are of same computational complexity, but feel very different in terms of expressivity. So for example, RDFS and EL plus are both polynomial time logics, but EL plus feels more expressive. And as we'll see, it's also harder to deal with. So that's the logic aspect. All of these logics, well, other than FOL, which is first order logic, are still relatively inexpressive. But as you see, they're tricky enough to deal with. Then the next column is about transfer. And transfer means, well, can you actually train on one knowledge base, and then the system can also work on knowledge bases it hasn't seen before. So we have an out of vocabulary problem here if we want that. And yes, we would like to have that, because only if we can do this transfer, we can claim that the system actually has learned to reason, right? Like we can reason. And of course, also for applications, you want that, because training is very expensive. So you would like to train this once and then use it for all kinds of different knowledge bases. So yes, and the transfer would be nice. Generative is, do you have a system that actually does, is based on naturalization and not just on querying for yes or no answers? So we want a yes here as well. You can think about scale. Well, these labels are a little bit moderate. How big are the knowledge bases you can deal with? Of course, what you would want here is high, right? I don't think we're there yet. And then, of course, in performance, we also want high. Performance meaning how good is the reasoner after training. And you see that in particular, transfer and generative is not that often here. But this is the systems which Monireh will talk about in her second piece in particular. So what are we going to do? I gave you the intro. Monireh is going to talk about memory networks for RDFS. That is a classification system. Then Aaron is talking about LSTMs for EL+, and then we'll cycle back to Monireh, which talks about her most recent work on pointer networks, which is now the system which does transfer and generalize. And then Federico will look at the much harder logic, first order logic, with visual logic tangent networks. And I'll come back for a quick conclusion, and then we'll have questions if we have any. If you have questions, please feel free to put them in the chat, and I'll try to answer in chat. And I'll hand it over to Monireh now.
Thank you so much, Pascal. Hi everyone, I'm Monireh. I'm a senior cognitive software developer at IBM Watson, working on open source team. And here I'm presenting the work that I have done on generalizable neurosymbolic deductive reasoners. I have done most of this work when I was research PhD student at Kansas State University in DAISY Lab. Under supervision of Dr. Hitzler. As Pascal mentioned, we are focusing on the deep deductive reasoners, and the ideal thing that we are looking for is the deductive reasoner that do the deduction on expressive logics with transferable capability, and being able to generate all the outcomes, all the logical consequences in a massive scale. Today, I will present two of my work on this topic. First, I will start with memory networks that I have applied on RDF logics with transfer capability. The first one is not the generative model, and the scalability is moderate, and we got a high performance. In the next presentation, I will focus on pointer networks, and I will talk about that more. I have applied that on RDF and EL plus reasoning. It has the very good generalization capability, and it can generate all the logical consequences of the knowledge base that we have with moderate scalability and very good performance. Let's start with memory networks. First, I start from what is RDF deductive reasoning. So RDF is a very widely used standard for expressing knowledge graphs that uses node, edge node, or subject predicate object ripples to express the knowledge base. Here, for example, you can see the two instances that we have in our knowledge base, and we have set of inference rules that we can apply to the instances that we have. For example, here we have two rules, and based on those rules, we can get some logical consequences. As you can see here, we can infer another instance and add that to our incomplete knowledge base and make that more complete using logical deductive reasoning. Here are the set of, for doing deductive reasoning over RDF, we have 13 entailment rules. Here you can see some sample of those entailment rules. For example, the transitivity over the subclass or subproperty of, and using domain and range for getting new consequences, or typing and using the typing and subclass of for generating the new entailment, the new inferred triples. What is the focus of this study? Actually, problem with previous work that is if we train a deep learning system, so we want to be able to create a deep learning system that we apply them on a set of knowledge graphs, and we are able to apply them to completely new knowledge graph with in the different domain or different vocabulary. But most of previous work use embedding use the numerical representation of the name, the entities that we have in the knowledge base, and uses the similarity to and the induction to get a new set of triples that we can add to our knowledge graph. But what is the challenges that we should overcome if we want to get an generalizable knowledge graph reasoning? So we have out of vocabulary problem, and we shouldn't follow the similarity or relatedness embedding representation and those approaches in our approach. So the idea overview for this work is we have set of knowledge bases, and for each knowledge base, we want to we have a set of queries, and we want to give the query to the knowledge base, and based on what our network here, the memory network, based on our memory network, we want to be able to say whether we can infer that query triple from our current knowledge base or not. But we have selected memory networks, so we know that recurrent neural networks are very good for when we have a temporal structure, and the convolutional neural networks are working very well when we have a spatial structure in our data. But here we have a large knowledge base. We want to have out of order access to some of the triples that we have in the knowledge base. We have long-term dependency when we are doing multiple hop of reasoning, and the order doesn't matter to us in our knowledge base. And we know that memory networks have been applied very successfully to question answering on a story, and but still we know that memory networks have out of vocabulary problem. What is memory network? Memory network are neural networks that have external memory, and we have a soft attention over the memory through multi-hop computational steps. And using those multi-hop attention and lookups over memory, we can answer to the query that we have based on whatever we have in the memory. And the training has been done using the backpropagation. But as I said, we have a very important problem here, and that is that comes from the ungeneralizable capability of the memory network. For that, we have used the normalization by syntax normalization. I mean, we are renaming everything that we have in the knowledge graph to set of predefined entity names, and we just keep the RDF and RDFS name space vocabulary. For example, here you can see that we keep RDF type here, and we change Barack Obama and politician to another predefined names that we have in our knowledge base. If we have Barack Obama in the same knowledge graph, then we use the AB again for Barack Obama. But if we have that in another knowledge base, it doesn't matter, because we don't want to learn the representation for Barack Obama. We just want to learn the representation with whatever we have in our knowledge graph. And based on that specific knowledge graph, we want to be able to do the reasoning. And here is the structure of our memory network. So we have normalized our vocabulary. We have put that in our knowledge base. We have multiple lookup tables that uses that normalized vocabulary. Then using querying to these lookup tables, we are gaining the triplet representation for each of triple that we have in our knowledge base, and then using positional encoding, because the subject, object, and subject, predicate, and object order matters. We are encoding everything that we have in the knowledge base in two different representation: input representation and output representation. We are doing the same for our query. And then here is our single layer model, memory network model. So we are giving the query to the model, and also we have our knowledge graph here represented in the this box. And then using the dot product of the query over the memory, we are finding the attention of the query over the memory, and we are doing that over multiple steps. I will show you in the next slide. And then using the weighted sum of the memory, using this attention, and finally applying, multiplying that with our weight matrix and applying softmax, we can predict whether we can infer that triple from the knowledge graph or not. You can see here we have three-hop attention model where we apply this attention multiple times, and we are updating our query multiple times until we find the answer. And here is our results. So you can see that when we have a training set and we have another test data set from another domain or vocabulary, we have very good accuracy for the baseline. We have used the non-normalized version of our data set. And you can see that we have a significant boost in our performance using the normalized version of our data and using the normalizing in our memory network approach. And also to get a better understanding of how our model works when we have multiple hops in our reasoning. We have actually created another synthetic data with multiple hop with the long chain of reasoning, and you can see that we don't have that much good accuracy when we are increasing the number of hops, and that's because if you can see the distribution of our training set, you can see that in our training set we don't have that much long reasoning chain, and we know that that's the case for most of the real world data set, at least the one that we have created here. And here is the PCA representation of our embeddings, and you can see that the embedding makes sense. For example, domain and range are in the vicinity. We have subject, predicate, and object together, or back, sequence, alt, and container together. So we constructed memory network for emulating the symbolic deductive reasoning, and using normalization approach, we enhanced the transfer capability here, and we show the efficacy of our model for cross-domain and cross-knowledge graph deductive reasoning. So I will hand over to Aaron for his presentation.
Okay, sorry, had to click a bunch of buttons. Hi, I'm Aaron. I'll present about my work on completion reasoning emulation for EL+. Oops, excuse me. The motivation for this work it was that we wanted to do something a little bit different. So, you know, we kind of all know that neural networks are great at learning the correct answers to data that we input to them, but a lot of neural symbolic systems are closer to deep learning than logical systems because they do this kind of training like you would do in deep learning rather than learning something like semantics. But when you say semantics, it's not really clear that this is a good idea or how you would even train a network to learn like the structure of reasoning rather than just the answers of the reasoning process. So in order to study this, we came up with some research questions. Primarily, we wanted to make a system that can emulate the behavior of the reasoner and train it to do this rather than training it to learn the answers of the reasoner. And so connected to this, we're trying while we're doing it to avoid embeddings that might make it more black box or inject semantics into things that we didn't intend. Also, it's necessary to use arbitrary numerical names like you would in a symbolic system. Interestingly, if we have like a symbolic reasoner, you should be able to stop it in the middle and see what it's doing, unlike a neural network. So there should be a way, if we're learning structure correctly, to put a midpoint in and then see what it's learning or figuring out by that point. And finally, it's not clear in this case when we're learning structure whether F1 score even makes sense anymore. So we'll look at that a little bit. The logic we're using for this is EL plus, the description logic. So you have a knowledge base with a set of concept subsumptions and role subsumptions, and you're allowed to make use conjunction and existential, but you will notice that you're missing, in like you would typically see in a description logic, things like negation, universal quantifiers, so on and so forth. So effectively with EL plus, the simplicity of it means you can apply rules like these ones shown here, and basically on a loop similar to an RDF reasoner, and then it will reach completion, which when it derives all of the consequences on the form of the form on the right. In order to take EL plus data and put it into excuse me, the system, and also inject this intermediate state, we define supports. So as the reasoner goes, it's learning new things, and then it uses these new things that it learned to learn new things again. And so in order to put the data in, we need to find a way to kind of reverse this reasoner and find out what data you use to make these conclusions that are kind of in the middle. So the support, for instance, when it learns the fact in step 2, you can kind of like roll back the statements it used to use the original statements in the original knowledge base. And then these statements themselves can be put into, sorry, I'm losing my train of thought. Encoded into small quadruplets, because the normal forms of EL plus are all of these forms. And so, yeah, I'm gonna skip forward. I'm losing my train of thought. For our data sources, we used 2 separate things. So there's a sequential random generator. This is all synthetic data. This is very balanced because it guarantees the use of all the completion rules, and it's randomized in a different partition, but also connected. But it's totally synthetic. We also sample from SNOMED 2012, and this is real world data, but also the end result of that is it ends up with an imbalanced use of the completion rules. So it's much harder for the system to train and learn on this data. The LSTM that we used there are 3 different setups, and the reasoner steps that the EL plus knowledge base used are the sequences that the LSTM is learning. It is possible with the supports we defined to set up what's called a piecewise training. So you can kind of train 2 halves of a network instead of a whole deep system that just kind of does and you don't know what it's doing in the middle. This process is completion on continuous values, and it's not a classification problem because it's learning all of the consequences. So it's training with regression on mean squared error. The first architecture that we use is called flat, and it's basically just like a single layer LSTM default out of the box, what TensorFlow gives you, and then the only thing that's changing is the input size and the output size, and it's just directly trying to learn this. And predictably, this is not doing so well, although sometimes it's okay. The second system is the deep system, and this one, it's allowed to go from beginning to end on its own, but we tell it to have this dimensionality in the middle of the supports that the reasoner discovered. And finally, there's a piecewise system, which is identical in shape to the deep system. However, it stops in the middle. So the training is separated. And so you can train this second half with the actual answers that the actual reasoner knows are correct, rather than kind of letting it figure it out on its own. And so in these graphs, you can see the green lines are the piecewise system, the blue line is the deep system, and the red line is the flat system. And we have mean squared error over epochs. And it's very interesting to compare these, because normally you would just have a line of, this black box deep system is training, and okay, yeah, it's getting better at this point, but we don't know which part of the data it's good at or bad at. And clearly we can see, especially on the hard SNOMED data, that learning to train the sequence where it learns the knowledge base to the supports is much easier than learning the supports to the actual reasoner answers. And so this is very interesting and gives us more opportunities to investigate this type of network for NeSy. Sorry. For the synthetic data, we can see very nicely the kind of things that we're getting from this system, because it's because it's uniform, and often you can tell, like, it's getting really close. It's not actually getting right answers that often, but there's something that it's doing where it's learning the shape of these statements. So with SNOMED, it's harder because the data is more dense. But at least with these, there are words. It's not just randomly generated numbers. For our evaluation, we use Levenshtein distance to do string distance. However, edit distance measurement fails to account for near misses, like we saw in the previous slide with the synthetic data. And this contributes to what might be, I don't know, inaccurate evaluation, because we have a lot of things that are getting really close, but if you look at only F1 score, like almost none of them are correct. Or some of them are correct, but a bunch of them are close but not flagged as correct. So this doesn't totally solve it, but we have a custom predicate distance which takes these actual numerical values into account when it's measuring how far away they are from each other. This chart is much blurrier than I thought it would be, but you can see on the synthetic data, when the problem is easier for the system to solve, it looks like the deep system is doing a lot better. However, when you make the data much more difficult, like in the SNOMED one, it's no longer clear that it's doing a lot better. And so, and sometimes the flat system, which is the naive kind of do it, in the one shot, is even doing a little bit better. When we look at the actual distances rather than the F1 scores, it gets even less clear, because still the deep is doing better, but on the hard data, it's all over the place. So in a sense, this kind of reinforces the fact that these neural symbolic systems need their own, type of evaluation and structure and things like that. And so it's not clear exactly what that should be or how we should figure it out, but something is, I'm losing my train of thought again, I'm sorry. Yeah, I'm gonna wrap up now and hand it over back to Monireh. Yeah.
Thanks, and I think it's Monireh next with her second part. I think we're running a little bit behind schedule, so let's just make sure we have enough time for Federico in the end.
Yeah, sure. So Pascal, please stop me if I go over time.
Okay.
So here is our work on the generalization capability of pointer networks for RDF and EL+ reasoning. Here we are using input-output mapping sequence to sequence model for generating the inferred knowledge graphs. And for that, we are using pointer networks. Why we have selected pointer networks? Because they have been applied successfully to many combinatorial optimization problems, like traveling salesman problem, which is NP-hard, and Delaunay triangulation convex hull problem, and also many natural language processing problems that we have out of vocabulary problem in those tasks, or rare vocabulary problems like text summarization, code completion, and dependency parsing. But what are pointer networks? Pointer networks are the kind of neural network that point to input elements. So in the decoding part, we are pointing to input elements. That is the way that attention works, pointer attention works in pointer networks. For example, here you can see that we have two statements here, and we want to entail another statement, a subset D. Here is a regular sequence-to-sequence problem, which can also use the attention. But in the pointer networks, when we want to generate the output, instead of generating the output based on the context vector and that we have in the decoding part, we are actually pointing out to the input, and we are generating the output based on their position in the input. For example, A goes to 1 here, which is A here in the input, and for generating subset, we have that here, so 2, and finally D in the 7th position. That's the way that pointer network works. And the difference between this one and Botna's additive attention is we don't find the weighted sum of the hidden representation of the input and giving that to the output. We just find the softmax attention of all the inputs that we have for generating the output in the pointer networks. The research questions that we want to answer based on the pointer network is, first, can we do the logical deductive reasoning using pointer attentions? Which is the first work that uses, our work is the first work that uses pointer network for doing so. And we want to also compare that to other attention-based sequence-to-sequence models, for example, self-attention-based one like the popular transformer architecture. And we want also to see how well do pointer networks do the task of transferring, performing well on completely new knowledge graphs. The data sets that we have used, the first one is EL+ dataset, the one that Aaron had used in his experiments with different sizes and with moderate difficulty. And for RDF, we have used the one that has been used in McNee and Hendler's work, the Lehigh University benchmark and real-world scientist dataset from the DBpedia. And our baseline, as I said, transformer, LSTM decoder instead of pointer LSTM decoder as an ablation study, graph for translation, which is the previous state of art in RDF reasoning, the McNee's work, and Piecewise LSTM that Aaron presented now. And here is our result. You can see that we have 99% accuracy using pointer networks over the RDF. The state of the art was 98%, and we have 73 and 49 and 68 for ER logic, and the previous state of the art the result was not comparable with this one. And in terms of the generalizability, we have trained our pointer network on one knowledge graph and applied that on another one. And you can see that we still have a very good result. Just to emphasize on another thing, so you can see that the transformer have not shown very good result, and also the subvortex, when they are using the subvortex encoding, the result is the best. And the reason for that is transformers are very embedding based approaches, so they are working well because they can find a very good representation for the terms that we have in our knowledge base. And when, for example, we are using the subvortex, we can generate the best embeddings. And that's why they are not actually working well when we have a normalized set of data, because in that case, the representation doesn't matter because we are changing the names, and we don't want to get the symbol related related embeddings. And when we change that to the subword, at least we have the better presentation and the result is better. And the result for LSTM without using the pointer network is not acceptable at all. So here was the summary of our contributions. So we introduced a novel paradigm for viewing a symbolic reasoning problem as a pointing problem, pointing to the input and putting all the terms together and generating the output. This was the first time that someone had used pointer network for reasoning. And our proposed approach was capable of transferring to new domain and new vocabulary. And it shows the reasoning capability of pointer networks as opposed to just learning the embedding and using the induction-based learning. And we actually got the state of the art performance for both EL plus and RDF reasoning. So I will hand over that to Federico for his presentation.
Hi, yes, thank you very much. So let me share my screen and tell me if you can see my slides.
Yeah, looks good.
Sounds great. So hi, everyone. So excited to be here to talk about this. Let's get into this. So today I'm gonna go over logic tensor network. My talk will be an introduction on logic tensor network. And also I'll be quickly talk about a bunch of things we have done over the years by, for example, extending logic tensor network with embeddings, but also talking a bit about scalability issues you might get into when you use logic tensor networks. So let me first start on what are logic tensor networks. So the idea is that we want to combine neural network with first order fuzzy logic, and what LTN does is to ground fuzzy logic into a vector space where we have values in 0 and 1. Also, we use neural network to actually somehow assign true values to the formula. And one of the cool features about logic tensor network is that they can learn from both data and rules. For example, you can have this kind of relationship, but also you can embed rules and use this to train the network. So you can actually introduce your domain knowledge into a standard machine learning problem, for example. And finally, the other interesting thing on the more explainability side is that you can somehow do inferences over rules after training. So say you train a logic tensor network model on ancestor and parent relationship, you can also test which is the truth score of this kind of axiom. So how do logic tensor network work? Well, the idea is that we start from this axiom, parent Susan n. What we do is that we represent the constants as point in RK. This can be trained during training process, or can be like pre-initialized with embeddings, as we will see next. And the parent, in this case, the relationship is going to be the neural network. Each predicate in the logic tensor network is a neural network that is gets in input these two elements plus a sigmoid, and the answer is going to be in 0, 1. These also work with more complex, let's say, formulas, where in this case we have the conjunction, we compute the two values, x and y, and finally we combine them with fuzzy operators. In this case, I've chosen the Gödel T norm, that is the minimum between the two, but you can get the sense that this can be applied to any kind of operation in fuzzy logic. How do we learn all this representation? Through backpropagation. So this is the key, let's say, feature of LTNs, because to learn, you just need to have a knowledge base. For example, here we have the knowledge base. Here we have the parameters of the neural network, and here are our vectors. If we have this as first input, so not parent Mark and John, this is represented as 1 because it's the negation minus the result for parent Mark and John, we might get 0.28, and we want to somehow maximize this value. And the idea is that we're going to use backpropagation to modify the weights of this neural network and the actual embedded representation of both Mark and John. The same goes with more complex formulas again. You can get the values of this one, apply the OR that in the Gödel fuzzy logic T conorm is the maximum. And again, you want to maximize this, modifying this and the respective vectors. So let me go over a few more things. You can also interpret and actually train on quantified formulas. How this is done in LTNs? Well, it's pretty easy. So if you have for all x of human of x, each variable in LTNs is associated to a domain sample. So instead of having an infinite number of count, we just have a finite domain sample. So if x goes over John and Paul, answering the question for all x human of x is defined as having an aggregation operation over the human x predicate that can be the minimum or the average. And if human of John is 0.8, human for Paul is 0.9, then for all human of x can be the minimum, it is 0.8, or can be also like the average. It depends on which kind of formulation you want to use for this. Again, let me restate this fact that you can both use data and rules to train these, and this makes it like very useful to embed somehow knowledge into this. And the overall idea is that you train this on a best satisfiability task where you learn the representation of vector for the constant parameter of the predicate, such as that the axioms you have are satisfied in the best possible way. Assume you have parent and Susan. We expect the network to learn the representation for n, Susan, and parent in such a way that they predict a value close to 1. And this is somehow the general idea behind the training. Last thing, very important, is that we can do after training inference. So it's somehow explainable. Suppose we trained on a data set of parents and ancestral relationship. After training, we can test on whatever combination of axiom we would like to test. Finally, going to the scoring, this is just for reference. One thing you want to say that the way LTNs deal with this computation is by concatenating the arguments of the predicates and pass them to this tensor operation that is from a 2013 paper at NeSy. But we'll just go over this, the idea that you can compute this and use this on higher variety predicates. Finally, the good thing is that with logic tensor network, you can deal with complex formula and somehow use the neural network to interpret recursively complex formula in which you combine stuff from ground up and get the final result. And this makes it very useful. There are different applications for logic tensor network. You can use it for classification, for clustering. And this is very important because it allows you to tackle standard machine learning problem, but also have this kind of property of introducing domain knowledge, so a logical theory on it, and get better results on any kind of task you want. What I'm going to show you now is this kind of logic tensor network with embedding that is an approach we tested for somehow extending the way of reasoning. So suppose we have this kind of axiomatic knowledge. We know that cat is a species, tiger is a mammal, and the penguin is a bear. We know some universally quantified axiom. We cannot infer something about cat because obviously there's not enough information to do this, but we might have access to what we call distributional knowledge. So the fact that the cats and tiger are more similar than cats and penguins. And eventually, if we know this, we can somehow infer that cat is a mammal, or let's say somehow induce the cat is a mammal based on the similarity, but also that cat is an animal because we have the universal rules. So we try to put these words together, and the general idea is that we start from word2vec. You probably already know word2vec. It's just a very simple way of devising representation of words from a corpus. So you have word2vec, you study the co-occurrence of words into text, and you generate the vector representation. In our case, K is what you want, of words. And the general idea is that you will have similar words appear in similar context and have similar vector eventually. So we use neural models to do this, and we can do this also to generate entities. And this is what we're gonna do. So we are gonna embed in the LTN network the vector representation of the entity, the DBpedia entity in our context for cat, and use this to do inferences in the way we talked before. So we created this simple knowledge base about species and subclasses, and we're gonna test on a knowledge base completion task. It's a very reduced set of things that we wanted to test. We use entity embeddings from Wikipedia. We have some axiomatic knowledge that the model can use to learn. And the task is the one I've shown you before. So we want to infer something, for example, about cat, even if cat is not present in our original axiomatic knowledge. So this is a standard example of training and testing. PSL is probabilistics of logic. We compared our LTN plus entity embeddings with a deep neural network that use entity embeddings, and it seems to work efficiently well. But remember, it's comparable, the result, but logic tensor network have the explainability part on their hand. And also we can do a zero-shot prediction on novel entities because our input is just the new entity embedding that we have in the knowledge base, and we can do this kind of prediction. And again, logic tensor network with entity embedding seems to work well on this task and comparable. But also one thing I want to stress is that we have this explainability part. So after training, we can go over the axioms and see the prediction and analyze what the model has learned that wasn't in the training data. For example, that an eukaryote is definitely not a bacteria, or at least it's very, it tends to be true as a predicate. Let me go finally over on the last part, that is the scaling part. So the question left to answer here is, how long does it train to train the logic tensor network when we have a lot of predicates and a lot of contests with different varieties? So we generate a bunch of random predicates with a bunch of constants, and we extend the variety of predicates. For example, we test the training of 4 unary predicates with this kind of combination for 4 different predicates. We do the same with binary predicates and with ternary predicates. And we train with different number of contexts. The only thing I want to show you is that the complexity seems to increase exponentially with the number, variety, and the actual number of contexts, because to train this in a very somehow constrained setting takes more than 6,000 seconds. So when you use logic tensor network, you need somehow to keep in mind that there might be this kind of issues that you need to find a way to deal with by maybe reducing the variety of your predicates, or also like considering what can be an alternative. Yeah, thank you. I'm happy to answer questions if you have them.
Thanks a lot, everybody. And we're essentially out of time, so I'm not going to put up a slide for the conclusions, but let me just say a word or two. So one of the things I think which became apparent from which could be a takeaway from kind of what you presented is, these are hard problems. As some have noted and discussed, some systems are kind of, they beat a random guesser, but not much more. Others scale really badly. Some do much better. And I think the pointer networks piece, which Monireh has presented, is probably the best we can currently do, because it does transfer and generalize. However, the logics are still rather simple. And while, for example, the memory networks piece can deal with knowledge bases having 1,000 triples, that's still not enough for practical applications. So there's actually a lot to be done here. Pushing scalability is one thing. Pushing the expressivity of the logic is another one, and then of course also pushing accuracy while still having transfer. So there's quite a bit of work to be done here, which is rather exciting. But one of the things which for me in particular is exciting is that we are now looking at problems which 15 years ago in the neurosymbolic realm were just impossible. There was no chance to do this before the advent of deep learning. So this is rather cool. All right, we had quite a lot of questions answered in the chat. I'm just trying to take the last one by Till. which I haven't answered to yet. You should notice a decline of performance for large signatures. So that's a good point. That we haven't been able to test that out. Because what we need to do, well, for the memory networks approach at least, the situation was that we actually had to settle on an input size, a maximum input size. So that kind of didn't allow that. That may be different for the pointer networks, but that needs to be tested out. Yeah, I think it makes sense what you're saying, that there is a trade-off between signature size and training time needed, probably. Yeah, but things we need to look into. All right, I think we're at the end of the time. If you have further questions, things you want to know, please just send us emails. We're happy to correspond with you. And thank you all for joining the session and for being here. And happy to hear from you. Thanks a lot, everybody.